400 years. That's how long we've been watching Jupiter. Galileo pointed a handmade telescope at it in 1610. Since then, thousands of astronomers, hundreds of missions, billions of dollars in equipment, all aimed at the same planet. The biggest one we have, the most photographed, the most studied gas giant in the history of science. And in 2016, when we finally sent a probe close enough to look it directly in the face, scientists didn't recognize it. The researchers who had spent their careers studying Jupiter looked at the first images from its poles and genuinely could not match what they were seeing to any model, any simulation, any prediction they had ever made. 4 centuries of observation. Every model we built was wrong. Every assumption we staked careers on collapsed. That was the first failure. There were 4 more waiting. We thought we knew what Jupiter looked like. The bands, the swirls, that 400-year-old red storm sitting in the southern hemisphere like a bruise that never heals. We put it on posters. We named its features. We built entire atmospheric models around the patterns we could see from Earth. Then Juno swung into polar orbit, the first spacecraft in history to look at Jupiter from above, and sent back images of the North and South poles. What it found was nothing like the planet we thought we knew. No bands, no order. Instead, dozens of cyclones, massive and tightly packed, locked in geometric formations around both poles, each one between 1,400 and 1,800 kilometers wide. The South Pole has 5 of them arranged in a pentagon. The North Pole has 8, orbiting a central storm in near-perfect symmetry. Each one of those cyclones covers more surface area than the continental United States. Some are wider than the entire Atlantic Ocean. They've been sitting there holding formation for years. That was just the outside. For decades, scientists were split into 2 camps about what sits at the center of Jupiter. Camp 1 said Jupiter formed around a dense rocky core. Ice and stone clumping together first, gravity doing the rest, pulling in hydrogen and helium over millions of years until it became the giant we see today, a pearl built around a grain of sand. Camp 2 said there was never a core at all. Jupiter collapsed directly out of a gas cloud, no solid center, just gas all the way through. Both camps had math. Both had careers staked on the answer. Juno made both of them wrong on the same day. The data came back showing something neither side had ever proposed. A fuzzy core, not solid, not absent, something in between, a region where heavy elements don't form a defined center, but instead dissolve outward, gradually blending into the surrounding gas with no clear boundary. Spanning approximately 130,000 kilometers, nearly half the planet's total radius. When the results came in, researchers immediately reached for the most obvious explanation: a massive collision early in Jupiter's history, shattering a once solid core and mixing the debris into the planet's interior. So they ran the simulations, supercomputers modeling every possible impact, different sizes, different speeds, different angles, hundreds of scenarios. Every single one failed. In every simulation, the heavy material did the same thing. It scattered on impact. Then it slowly sank back down, settled, rebuilt the boundary, every time, without exception. The math kept returning the same answer. A dissolved core is physically impossible, and yet Jupiter has one. Jupiter's magnetic field is the largest single structure in our solar system. It stretches 650 million kilometers behind the planet, past Saturn's orbit. If you could see it from Earth, it would appear twice the size of the full moon in our sky. And for years, we thought we understood it. Fast rotation, liquid metallic hydrogen deep in the interior, simple dynamo process. Juno built the most detailed map of it ever made, and that map immediately invalidated the explanation. The northern hemisphere is 3 to 4 times stronger than the southern. There are 2 magnetic south poles. There are intense localized regions where the field concentrates in ways that have no clean theoretical cause. And then there's the Great Blue Spot, a magnetic scar near Jupiter's equator where the field is unusually dense. Juno watched it across multiple orbits and found something that had never been observed on any planet before. The magnetic field was moving, shifting, drifting westward at roughly 3 centimeters per second, dragged by Jupiter's deep atmospheric winds. Scientists called it secular variation, a first for the solar system. But here's the fatal problem. The fuzzy core, the discovery that was supposed to eventually explain the magnetic field's strange behavior, made it more broken, not less. Modeling the interior with a fuzzy core produces a magnetic field that looks nothing like what Juno is actually measuring. We have better data than we've ever had, and we understand less than we thought we did. Juno was designed to die young, 20 months in orbit, then a controlled plunge into Jupiter's atmosphere. That was the plan. The radiation belt alone, at peak equivalent to 20 million chest X-rays per year, was expected to slowly destroy its instruments from the inside out. Instead, the radiation levels near Jupiter's poles came in 10 times lower than predicted. The spacecraft that wasn't supposed to survive its own mission kept going, into an extended mission that sent it where no probe had gone before, the moons. Ganymede. Scientists expected to confirm oxygen in its thin atmosphere. They found water vapor instead, forcing a revision of atmospheric models for every icy body beyond the frost line. Not just Ganymede, every one of them. Europa, up close. The highest resolution images ever taken, at 256 meters per pixel, of its fractured surface revealed something unexpected. Evidence of brine reservoirs trapped inside the ice shell itself, not just in the ocean far beneath it. Pockets of high salinity liquid expanding under pressure, cracking through ice that's over 10 kilometers thick. And Jupiter's lightning, a mystery sitting unsolved since Voyager passed through in 1979, finally got an answer. The flashes weren't coming from water storms deep in the atmosphere. They were coming from somewhere far too cold, below minus 88 degrees Celsius, for liquid water to exist. Because they weren't water storms. They were ammonia-water hybrid clouds, where ammonia acts as antifreeze, keeping a liquid mixture stable at temperatures that should freeze everything solid. And the hail falling out of these storms isn't ice. Scientists are calling them mush balls. Jupiter is raining slush. Juno was completing a routine flyby of Io, Jupiter's innermost large moon, the most volcanically active world we've ever found. A surface so constantly reshaped by eruptions that impact craters form and disappear within decades. Io ejects 1 ton of material into Jupiter's orbit every single second. On that day, the instruments lit up across the board. Hundreds of volcanoes scattered across a region spanning 65,000 kilometers roughly 5 times the diameter of Earth, erupted simultaneously. Together, the synchronized timing suggests they're linked. One vast network of underground lava channels, pressurizing, releasing, cascading across the Moon's interior in a single coordinated event. Juno was supposed to be dead by now. It survived its first mission, then its extended mission. Then a government shutdown froze the decision on its fate, and NASA went quiet. Weeks passed, months, no announcement. Then, without ceremony, they published new data. And at the bottom of the paper, a single line: Juno will complete its 81st flyby of Jupiter. A probe engineered for 20 months is now in its 5th year of extended operations. We sent it to answer questions about Jupiter. Instead, it became the question. Because here's what 400 years of watching and one probe actually proved. The models were wrong, not partially, structurally. At every layer we looked. The poles don't behave the way physics said they should. The core doesn't exist the way either theory predicted. The magnetic field doesn't work the way our models described. The moons don't look the way we expected. The storms don't fall the way water should fall. That gap has a name. It's called Jupiter. And we still don't know what's inside it. The probe is still transmitting. The data is still coming in. And every new orbit is producing results that don't fit the model. We weren't wrong about a few details. We were wrong about the planet.